So John MacQuarrie, our final speaker today, is from University Federal de Minas Gerais. He did his undergraduate in University of St Andrews and Scotland, and then PhD in Manchester in England. Well, he was postdoc in Bristol and UNB, and now is professor in University UFMG. John works on profinite groups and pseudo-compact algebras, and today he's going to talk about block theory for profinite groups. Please, welcome.
Thanks very much. Thanks, Christina and Misha. And Misha for the invitation and for organizing this session. It's a pleasure to be here. And I love these introductions. They're so, I feel so important. Okay, I'll talk about block theory for profinite groups. It's a part of the representation theory, modular representation theory of profinite groups. So first I'll tell you a little bit about the block theory of finite groups. And during the first part, I'll tell you what the defect group of a block is. And then in the second part, we'll talk about blocks whose defect group is cyclic. And then in the third part, we'll generalize the first two parts to profinite groups. So this is work with Ricardo Franquise, who finished his PhD with me this year. Okay, so what's block theory for finite groups? The general setup will be G is a finite group and K is an algebraically closed field. So in its most basic form, the question of representation theory is simply what are the finitely generated KG modules? So let's first look at the case where the characteristic of the field is zero. In this case, it's sort of at least morally easy. Maschke's theorem says that the group algebra KG is semi-simple. And so the Artin-Wedderburn theorem says that KG is a direct product of the simple algebra, of simple matrix algebras MNK. Remember that I'm supposing that K is algebraically closed. Okay, so let's the method I want to do to understand the modules for KG is to study first the modules for each of these factors. So what is the factors are the matrix algebra, and each matrix algebra has a unique simple module up to isomorphism. You can think of it as a column of the matrix, if you like. And then every KG module is just a direct sum of the modules for these factors. Okay, and so if we understood the modules for each of the factors, and then we understood all the modules, because every module is a direct sum of modules for these factors. Okay, I'm more interested in the case where K has characteristic P, and then usually KG is not a semi-simple algebra. If G at least has a cyclic CeLO P subgroup, then there are only finitely many indecomposable modules. But usually, in the vast majority of cases, there will be infinitely many indecomposables, and the category of modules will usually be, in a formal sense, very difficult. Okay, but nevertheless, the vague plan I gave still makes sense. KG is a direct product of indecomposable algebras, B1 times B2 times blah, 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 up to Bn. And KG modules can be uniquely decomposed corresponding to these factors. So a module U is U1 plus U2 plus U3 up to UN, where U1 is a B1 module, U2 is a B2 module, and U up to UN is a Bn module. And so the representation theory of KG splits up as the representation theories of these factors individually. Okay, so this means we can study the representation theory of KG one factor Bi at a time. So these Bi are called the blocks of the group G. Okay, so the block theory is split your algebra up into a product of blocks and study the representations of the blocks separately. Okay, Here's a simple example to show that what might happen is that some blocks are easier than other blocks. So let's look at a small example. Let's take K to be a field of characteristic 2 and G to be the symmetric group on 3 elements, so the non-abelian group of order 6. Then KG is not semi-simple because the characteristic of the field divides the order of the group. But as an algebra, the algebra KG is isomorphic to a direct product of two algebras. It's isomorphic to a direct product of the 2 by 2 matrix algebra of dimension 4 times the algebra Kx of polynomials factored out by x squared. So it's a 4-dimensional simple algebra and then times a 2-dimensional non-simple algebra. And so the only difficult part of KG is this second red block, KG over x squared. Okay, so how do we construct the blocks? The blocks of G are constructed using idempotent. So here are some simple definitions. An idempotent is central if it lives in the center of KG, which is to say it's central if it commutes with every element of the algebra KG. And it's centrally primitive if it's central, but it can't be decomposed as a sum of central idempotent. So it's centrally primitive if it's central, and it cannot be written as a non-trivial sum of orthogonal central idempotents. So these idempotents, these centrally primitive idempotents, are going to be the identity elements of our blocks. Okay, and so for this reason, we'll call a centrally primitive idempotent a block idempotent. Okay, so how do we form the blocks? We can write the identity element of KG uniquely as a sum of orthogonal block idempotents. So I write 1 times KG equals E1 plus E2 plus blah, 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 up to En. And then the block BI is by definition KG times the idempotent EI. And so since the idempotent is central, this is an algebra, and the identity element of this algebra is EI. Okay, so the block BI has identity element EI. Okay, so I said that some blocks are easier than others. So the example I gave, we had 2 blocks, and one was simple and one was not simple. But what we would like is a slightly more sophisticated way to measure the difficulty of a block. What we're going to do is, given a block B, we're going to define a subgroup D of G. And the easier the subgroup D is, the easier the block B is. This is the philosophy. So to define, in order to define this subgroup D, we need a sneaky tool, which is called the relative trace map. I'll tell you what that is. Okay, so this is some sort of obvious observations. A subgroup H of G acts on the algebra KG by conjugating. So the element little h acts on the element x of KG by sending x to h times h inverse. So this is clearly an action, and we're going to be interested in the h fixed points under this action. Okay, and observe that block idempotents, remember that block idempotents are elements of the center of KG, which means they commute with everybody, which means that conjugation acts trivially. And so the block idempotents are elements of the G fixed points of KG. Okay. So what we're going to do is take a subgroup and define a map from the H fixed points of KG to the G fixed points of KG. What does this map do? It takes an H fixed point. Can you guys see my little hand?
Yes, we can.
Yeah. Okay, thanks. So it takes an H fixed point X and sends it to this sum. It's the sum indexed by a set of left coset representatives of H and G of the element X conjugated by G. And so if you had a bit of paper in front of you, you could easily check that the trace from H up to G of the H fixed point X is indeed a G fixed point. Okay, so what's the definition of a defect group? Let B be a block with block idempotent E. Then a subgroup D of G is said to be a defect group of B if the block idempotent E is in the image of the trace map from D up to G, but D is minimal with this property. So if I have a proper subgroup of D, then E is not in the image of the trace map from H up to G. Okay, it's the smallest subgroup with the property that E is in the image of the trace map from D up to G. Okay, so that's a definition. To give a very vague idea of how to use this definition in practice, let's prove that defect groups are always P subgroups of G. Okay, so this is my clue. D is a P subgroup of G. So how's this proof going to work? I'm going to take a CeLO P subgroup of G, and it affects my idempotent. What I want to show is that E is in the image of the trace map from P up to G. Okay, so I'll show that E is in the image of the trace map from P up to G, and then D, because D is a minimal subgroup having the property that E is in the image, that implies that there must be a D contained inside P, and in particular, the defect group is a P subgroup. Okay, so the task then is simply to prove that when P is a CeLO, E is in the image of the trace map from P up to G. Okay, so E is an element of the center. It's a G fixed point of this action. Any point that's fixed by G is clearly fixed by subgroups, and so E is in the P fixed points of KG. And so let's just apply the trace map to the element E. What happens? We get the trace from P up to G of the element E is by definition the sum over a set of coset representatives of P and G of E conjugated by G. But E, remember, is a G fixed point already, and so when I conjugate, I don't do anything. And so this sum is just simply a sum of the index of P and G copies of the idempotent E. Okay, so that's kind of close to what I want, right? What I'm looking for is the element E, and what I have is a scalar multiple of E. But now we use that P is a CeLO. The fact that P is a CeLO means that the index of P and G is co-prime to P, which means it's non-zero in the field K. And the field K, remember, has a characteristic P. And so since this element is a co-prime to P, I can divide by it. And so I can apply the trace map to the element E divided by the index of P and G, and I get the index of P and G divided by the index of P and G times E, which is E. And so I found E in the image of the trace map, and this proves that the defect group is a P subgroup. And I just mentioned in passing that this is absolutely standard business. The hard part of modular representation theory is always that you can't divide by the number P when the field has characteristic P. Okay, so this is the first sort of a profound theorem of block theory. It's called the Brouwer correspondence. It says that there's a natural bijection between the blocks of G, whose defect group is D, and the blocks of the normalizer of D, whose defect group is D. This is an example of what they call a local global theory, local global theorem. So local global in the context of modular representation theory, global means to do with G and all its subgroups, and local means to do with P subgroups and their normalizers. And so the question is always, how much about the group G can we determine from the P subgroups and their normalizers? And so this is a local global theorem because it restricts from the case of G to the case of the normalizer of the P subgroup D. Morally, what it's saying is, it depends on the question, of course, but morally what it's saying is, you can start with a block, restrict to the normalizer, and then suppose that your defect group is normal. And as you can imagine, that's very helpful sometimes. Okay, so let me tell you what I mean by easy defect groups. I said that when the defect group is easy, then the block is easy. So here are some examples of easy defect groups. The defect group is trivial if and only if the block is simple. And then this is the part I want to talk about in the second part of the talk. It's the great victory of block theory was to classify the blocks whose defect group is a cyclic subgroup of G. So this is work of lots of people, including Brouwer, Dade, Janos, Kupisch, and others. It's a a long project. More recently, the blocks' defect group is C2 times C2 were understood. That's work of David Craven, Charles Eaton, Karen Erdmann, Rada Kessler, and Marcus Linkelman. And then just mentioning in passing that another easy class of groups is the class of abelian groups. And blocks whose defect group is abelian are just filled with extremely difficult structural conjectures. So the most famous of these is called the Brouwer's abelian defect group conjecture. I can even tell you what it says. Harder is to prove it. It says that if you, okay, so we have a block for G, and the Brouwer correspondence says that there's a corresponding block for the normalizer. Okay, there's a block for G, and it corresponds to a block for the normalizer of D. Okay. Oh, sorry. There's a block B whose defect group is D, and it corresponds to a block of the normalizer of D. So Brouwer's abelian defect group conjecture says that if D is an abelian group, and then these two blocks are derived equivalent. As far as I know, this conjecture is a very long way from being proved. Okay, so let me tell you how blocks with cyclic defect group are classified. Blocks with cyclic defect group are understood as algebras. They're what are known as Brouwer tree algebras. So I'm not going to give you the formal definition of a Brouwer tree algebra. What I'll do is show you how to do it in an example, and hopefully from the example it will be clear how it works in general. Okay, so we start with a finite tree gamma, and we embed the tree into the plane, and we're going to label the edges. And so I've called them S, T, U, and V. Now we choose one of the vertices, and we give it a multiplicity. So the multiplicity can be any positive integer. So I've taken the vertex of valency 3, can you see, and I've colored it red, and I've given it the multiplicity 2. Okay, so this is the Brouwer tree we're going to consider in our example. Okay, and so from this Brouwer tree, we're going to construct an associative algebra called B of gamma. Okay, so how does it work? Well, first I'll tell you how it works in general, and then I'll do examples. So the simple modules are labeled by the edges. So the simple modules are S, T, U, and V. And what this construction is going to give is the composition series of the projective. It's going to give the composition series of the projective modules. So it will give the composition series of each of the projective cover Px of the simple module X for each of the simples X. Okay, so the first composition factor, the top composition factor, is always X because it's the projective cover. And the bottom composition factor I'm also going to demand is X. And so the topmost composition factor, Px by rad Px, is isomorphic to X, and the bottom composition factor is also isomorphic to X. So we still need to decide who goes in the middle. And we'll decide who goes in the middle using the structure of the graph. And so the simple module X, remember, is an edge, and so it's adjacent to two vertices V and W. So what we're going to do is the following. We're going to first circle around the vertex V, and every time we bump into an edge, we're going to write down the simple module corresponding to that edge. And we'll just keep writing down the simple modules we bump into until we get back round to the edge we started. Okay, and so writing these composition factors starting at the top and working our way down, we get a uniserial module, which I will call PV. And now we do the same thing with W. We start at the edge X, and we go circling around the vertex W, listing all the edges that appear, and this way we get a uniserial module called PW. Okay, so that's almost all we have to do. I have to tell you what we do when the vertex is exceptional. If one of the vertices V or W is exceptional, then we're going to go around the vertex the multiplicity number of times. And so in this example, if either V or W is the red vertex, then I have to go around the vertex twice. Okay. Oh yeah. So then, okay. So then, what is going to be the the projective module. So it has x at the top, the projective cover of x has x at the top, x at the bottom, and then in between the radical of px over the socle is a direct sum of these two uniserial modules PV and PW that we constructed. Okay, so let's do some examples. Let's calculate the projective cover of PS. This is the easiest one. So notice I've labeled the two vertices on either side of the edge S. So let's first go around V. When we go around V, we don't find any other edges, and we get back to where we started without finding anybody. And so PV is the 0 module. When I go around W, I find T, and then I get back to the start. And so the only module I found was the module T. And so then PS, it has S at the top, S at the bottom, and then 0 plus T in the middle. So it's, in this case, it's a uniserial module, STS. Okay, so that was the and W. So going around in this direction, I come across S, going around V. And now W is the exceptional vertex, and so we have to go around it twice. So I'm going to go circling around the vertex 2 times, starting at the edge T. So I get V, U, now I'm back to the start, but I have to go around again. So I get T, V, U. And so PW is the uniserial module VUT, VU, and PT has T at the top, T at the bottom, and then the direct sum S plus VUT, VU in the middle. Okay, the last two I'll do a bit faster, U and V. So going around the leftmost vertex of U, I get T, V, U, T, V. And the rightmost, I don't find anybody, and so it's a uniserial module in the end, UTV, U, T, V, U. And finally, PV is VUT, VUT, V. Okay, so anyway, the point is that this completely describes the algebra. And then the theorem is that the whole point of this is that if a block B of Kg has cyclic defect group, then B is isomorphic to the Brouwer tree algebra of some Brouwer tree gamma. Okay, and I mentioned the only slight weakness of this theorem is that as far as I know, it is not completely understood which Brouwer trees correspond to blocks of finite groups. Okay, so that's what I wanted to say about finite groups. Let's make this profinite. Okay, so let G be a profinite group. I'm going to suppose we know what a profinite group is. Well, I mean, I can tell you, but if you don't already know, it won't help. It's an inverse limit of finite groups in the category of topological groups. Okay, we want to understand the representations of G over a field K. So first we need a ring. So G is by definition the inverse limit of finite quotient groups G over N. And each G over N, we know what to do. Each G over N is a finite group, and so it has a finite dimensional group algebra, Kg over N. And then we observe that K blank is a covariant functor in the obvious way, which means that the inverse system of finite quotients of G corresponds, when we apply this functor, to an inverse system of finite dimensional algebras. And then we're just going to define our group algebra, Kg, called the completed group algebra, to be the inverse limit of this inverse system of finite dimensional algebras. Okay, so it's a very well behaved object, and it's the right object to study if you want to understand the representation theory of the profinite group G. Okay, so let's construct the blocks. This was first done by Gabriel. Let E be a maximal set of centrally primitive central idempotents of Kg. So this set exists. And what's more, the sum of all these centrally primitive central idempotents is meaningful. This element makes sense in kg even though the sum is infinite. And furthermore, this equation makes sense. The sum of the centrally primitive central idempotent is the identity element of kg. And then, as you would expect, kg can be decomposed as a big product indexed by the centrally primitive central idempotent, the block idempotent, and the blocks are going to be kg times the idempotent e. So these kge are the blocks. Okay, a little bit less immediate is how to define the defect group of a block. So what we would like to do is use the trace map. So let's just try and naively use the trace map to define the defect group. So the trace map should be a map from the h fixed points of kg to the g fixed points of kg, and it would send the h fixed point h to the sum of conjugates of x indexed by a set of left coset representatives of h and g. The problem is that when h is not open, when h has infinite index in the profinite group G, then this sum is infinite, and this element really has no sensible interpretation. Okay, this element does not make sense as an element of kg. Where it does make sense is precisely when this sum is finite. So if h were open, this element would make perfect sense. And so what we can do is define the trace from Hn up to G whenever n is an open subgroup. Open subgroups, remember, have finite index. And so this is the trace from the finite index subgroup Hn up to G. Okay, and this will allow us to define a subset of Kg, namely what we call the O trace. O stands for open. The O trace, the O trace from H up to G is the intersection, is by definition, the intersection over the open normal subgroups of G of the images of the trace maps from Hn up to G, because when the trace map from Hn up to G is well defined. Okay, so this gives a well-defined closed subset of the G fixed points of Kg. But let me just observe that O trace Hg is not a map. It doesn't give you a way to take an H fixed point and define a G fixed point. It's only a subset of the G fixed points of Kg. But this is enough to at least define a defect group. So this is our first definition. The closed subgroup D of G is a defect group of the block B if it is minimal with the property that the block idempotent E is in the O trace from D up to G. Okay, so that's a definition. And then we can prove various facts. Defect groups exist. There are pro-P subgroups of G. As with finite groups, I didn't say, but as with finite groups, they're well defined up to conjugacy in G. And the fourth is just an extremely useful theorem for us. Of course, if the CELO of G is not open, then there's no way that the defect group can be open in the group G, and this can be quite tricky at times. But at least what is always true is that the defect group is open in a P-CELO subgroup of G that contains it. Okay, and so then we generalize the Brouwer correspondence. So let D be a pro-P subgroup of G that is open in a pro-P in a P-CELO subgroup that contains it. Then the blocks of G with defect group D are in natural bijection with the blocks of the normalizer of D with defect group D. I just mentioned in passing that this word open is necessary. If I replace the word open with the word closed, this theorem becomes false. But this word open is not a restriction, because we showed, this is number 4 here, that defect groups, all defect groups of all profinite groups have this property. And so it's not a restriction. Okay. I don't want to talk about the proof except to mention the trickiest part of it. So the hardest part of the proof was the fact that to prove the Brouwer correspondence, you really do need a trace map. All we have is a trace set. We don't have any way to take an H fixed point to a G fixed point. And so the hard part of the proof was to develop what we call a modified trace map, which really is a well-defined linear map from the d fixed points of kg to the g fixed points of kg. And this map applies to defect groups. Okay, so that allowed us to prove it. Let me show you a quick example before moving to cyclic defect group. Okay, so let's suppose that the characteristic of the field is 2. Remember that the algebra KS3 has one simple block, M2K. Simple algebras have defect group 1, and so the algebra M2K has defect group, the trivial subgroup. And then the other factor was the non-simple block KX over x squared. So being non-simple, that means that the defect group must be non-trivial, but the only other two subgroup of S3 apart from the whole group is C2. Sorry, apart from the trivial group is C2. Okay, so the profinite group we're going to consider is the infinite product of copies of S3. Then its 2 CELO subgroup is the infinite product of copies of C2. So then the blocks of Kg have the following form. What this is saying is morally that the blocks of a product of groups, are the product of the blocks of the factors. Okay, except that for groups we mean direct product, and for algebras we always mean tensor product. And so this is like a profinite version of the tensor product. Okay, so blocks of Kg have the following form. They're B sub I, a big infinite tensor product of Bn, where Bn is either M2K or Kx over x squared. And then the condition is that the matrix algebra, the simple algebra, can appear only a finite number of times. And so since it appears a finite number of times, I've marked the indices in which M2K appears as a factor and called this set I. And so this index is the block. So B sub I is a big tensor of these Bn's, where these Bn's are M2K precisely in the indices I. Okay, so Bi, what's the defect group? The defect group of the product is the product of the defect groups. And so the defect group is a big product of Dn, where Dn is 1 if Bn is the simple algebra M2K, sorry, and it's C2 if Bn is Kx over x squared. Now just observe that for each Di as above, there is a unique block of G having defect group Di. So I'm trying to get to the Brouwer correspondence. Okay, so because we don't want to get worried about sets of indices, so I've just taken my set of indices to be the first 2 elements of the natural numbers. And so my block B is matrices times hard part forever. Okay, so there's 2 copies of matrices, and then the rest is the hard block Kx over x squared. So then the defect group is 1 in matrices, 1 in matrices, and then C2 forever. Okay, notice that this defect group has index 4 in this CELO. I said that they always have finite index. Okay, so B is the unique block of G with this defect group D. The normalizer of D is, so the trivial subgroup is normalized by S3, and C2 is self-normalizing in every case. And so the normalizer is S3 times S3 times C2 times C2 times C2 times C2 forever. And so the Brouwer correspondence says that there should be a unique block of the normalizer having this defect group. And there is. I take, in the first factor, I take matrices. So I've got KS3 here. Here I've got KS3, I take matrices. And then from then on, I take the group algebra KC2. This is an indecomposable algebra, and its defect group is C2. So that's an example where the Brouwer correspondence worked out. Okay, so let's talk about blocks with cyclic defect group. So what's a cyclic pro-P subgroup? There are 2 options. It's either the finite group Z by P to the NZ, or it's the infinite procyclic group ZP. So I'll just tell you what happens in these two cases. So let's first look at the case where the defect group is finite. Then if D is finite, then B is finite dimensional as an algebra, which means that it's a block for some finite quotient group of G. So what this is saying is that the blocks of G with finite cyclic defect group, the blocks of profinite groups with finite cyclic defect group are precisely the same thing as the blocks of finite groups with cyclic defect group. Okay, so when you pass from finite groups to profinite groups, nothing new happens. It's a remarkably well-behaved situation. So that leaves us with the infinite procyclic group ZP. I was expecting this would be very difficult, and it turned out to be very well-behaved as well. The blocks with whose defect group are the p-adic integers ZP are insanely easy. So here's the result. If B has defect group ZP, then it is the Brouwer tree algebra interpreted in a profinite way, don't worry about the details, of a finite Brouwer tree of the following form. So it has a vertex of infinite multiplicity. Having infinite multiplicity means that when I go round the vertex, I'm just going to keep going round and round and round forever. Okay. But then the remarkable thing is that every edge has to leave from this unique vertex, this unique exceptional vertex. This is called a Brouwer tree of star type for obvious reasons. And so we understand them completely. There's no difficulty about what trees can appear. They're the stars. Let me just finish by I don't want to talk about the proof of these results. I'd like to just show you a fun little corollary. If B is a block with defect group ZP, then the global dimension of the algebra B is 1. If you're familiar with, I'm not very familiar, but if you're familiar with the homology of finite groups, then you'll know that a module for a finite group is either projective or very badly behaved. It's either projective or it has infinite projective dimension. Okay, this result here is saying that a module for the block B is either projective or it has projective dimension 1. These are the only two possibilities. So it's a situation very, very far removed from the situation of finite groups, but homologically it's saying that they're extremely well behaved as algebras. And the fun thing is just how easy this is to prove, given the result about Brouwer tree algebras. So let me show you the proof. Okay, so we need to calculate a projective resolution of the simple modules. So let's do the simple module S1. So being a Brouwer tree algebra, I know exactly the composition series for the projective cover of S1. So I just go S1, S2, S3, S4 up to Sn, then round again. S1, S2, S3 up to Sn, S1, S2, S3 up to Sn, and round we go forever. So this is the projective cover. And now we need to look at the kernel of the map from the projective cover onto the simple, and that's just the same module again, except that the top factor is not in the kernel. Oops. And so this is the module S2, S3, S4 up to Sn, S1, S2, S3, S4 up to Sn. So we're just going round and round and round, but starting at S2. And so this is the projective module, the projective cover of S2, which means that the projective resolution of S1 goes 0, S1, P1, P2, 0. And that shows that S1 has projective dimension 1. And similarly, all the simples have projective dimension 1. Okay, that was just for fun. That's all I want to say. Thanks for your time.
Thank you very much. Let's then call the speakers of today and of yesterday, of other days.